Good morning, Year 12. Hey guys, it's nice to see you. It's nice to see that everyone's waiting on the chat and everyone's already sent a message, which is really lovely. Thanks, guys. Do appreciate it. I'm just waiting for the video to start on my other side so that I know it's all functioning. It's interesting. I can look at the delay's about 20 seconds. There we go. I'm good. I'll close that window and leave the pop-up chat. Amazing. Right. So today, guys, we're starting work on energetics. So we had a look at the energetics GCSE test. You all did really well. It's really nice to see that you've got a really good base knowledge of what's going on here. And today we're going to be starting the A-level AS energetics. And we're going to be looking at heat energy changes. Right. So at this point, I'm going to share my screen and we can crack on. I like it. Go. I'm also going to do my usual trick of trying to disable my camera. I've started to figure out with this laptop, with its rather odd idiosyncrasies, how to prevent it crashing. God, I hope so. So if I don't have the video playing on the screen, fingers crossed it doesn't crash. Don't crash, don't crash. Yes, we're in. Amazing. It gives my laptop just that little bit more performance. Okay, we're in. I like it. Okay, guys, so energetics lesson 1. So today's lesson, I'm going to try and keep it short today because I just want this to be a nice general introduction because the main key thing here is recognizing definitions and understanding when enthalpies can't be measured. So the first thing that I really want to do is I just want to talk about, and this is where I'm going to switch to black, shrink my pen, give that a try. Okay, so the word enthalpy. So enthalpy. Now this word, I actually hate this word in chemistry. And the reason being is because I just don't feel like there's an awful lot of easy understanding in terms of the word. Because, you know, there are so many times in chemistry where they use good words like decomposition. I like that word because it's describing what's happening in terms of chemistry, and it's easy to understand. If someone says it to you, you can usually build it from base understanding, but the word enthalpy is just horrible. And so the word enthalpy stands for heat energy change. Heat energy change. And I want to just talk about this idea of heat energy. And now, by the way, there's actually a little bit more to this. Just talk about heat energy change. And this idea of heat energy versus temperature, those two things are very, very different. And we just need to make that really clear. So now, before I do that, before I drop into the difference in heat energy and temperature, I just want to continue to explore that term enthalpy. Because number one is, we know it's the heat energy change, and it gains a symbol. And that symbol is delta H. Yeah, now I actually much prefer that. That actually makes total sense because it's got a capital letter H standing for heat. Now that I like. And of course the delta, it's nice just to recall that that is a capital delta. Capital delta. And that delta in chemistry means change in. Now we also see it in maths, which is great. Now the next thing is to mention is that enthalpy at this stage, we now need to talk about the fact that in chemistry, we like to measure this. We are always attempting to see how much heat energy a reaction releases to the environment or absorbs from the environment. And now what we realize is that in order to measure this, we need to try and standardize it. Because I'm sure that you guys would probably already know that if you change conditions, then you change heat energy outputs. A great example for that is, of course, pressure. So now a change from GCSE to A-level is the realization that we need to try and standardize conditions. So now this enthalpy definition now picks up an extension in its definition. So instead of just being heat energy change of a reaction, this is now heat energy change at constant pressure. At constant pressure. And I now need to remind you guys, and it's always nice to see overlap within chemistry, of this symbol. So we now pick up this train station symbol. Yeah, and that train station symbol we have seen in calculations. And that stands for STP. Standard, and I'll convert that into real words, standard temperature and pressure. Standard temp and pressure. Now, in this particular case, the temperature doesn't apply. So now I had this argument recently with Oliver, this concept of, well, hang on a minute. If we're talking about temperature, heat energy changes, one of the things that they often ask you very commonly at GCSE is, what things do you need to keep the same in order to be able to measure the temperature difference, in order to be able to measure heat energy changes? And Oliver argued that temperature should be one of them. Now, this isn't true. For enthalpy, now just to really make that clear, yeah, for enthalpy, temperature doesn't really matter. Now, the reason for this is because we are measuring temperature changes. Yeah, we measure temps before, and then temps after. And what we, of course, calculate is therefore a temperature change. Yeah, a change in temp. And what it's nice to mention here is that, you know, if you do reaction A and you start it at 20 degrees and it ends at 25 degrees, yeah, I'm going to have a difference of 5. Now, what you'd realize there, of course, the answer is actually -5. Yeah, and you've got to be careful here because temperature changes, you don't really tend to talk about positives and negatives because, you know, it's a change in temperature rather than a, well, it's not, you can't really have a negative, well, you can have a negative change in temperature because it decreases, but you wouldn't really call it such. And I know that I'm switching the after to before. You know, when I'm going to measure, when I'm going to actually calculate it, I do 25 minus 20, the after minus the before. So, but the point I'm trying to make is if I then repeat the experiment and I do the experiment at 27 degrees, and I start, this is where me doing this is rather awkward, 20 degrees at the beginning, and then I do 25 degrees after, and I repeat the experiment at 22 degrees at the beginning, and where is it going to end? Well, if I've repeated the same experiment, chances are I'm going to achieve 27, and I will get the same change. Now, Oliver argued this with me. He was like, well, hang on a minute. You know, if I do the experiment at 50 degrees, and sorry, that should have been B, as repeat number 2, I'll put repeat, in fact, instead of doing A and B, I'll do repeat 1 and repeat 2. Yeah. And Oliver argued with me on this one, and he was like, well, hang on a minute. You know, if I did repeat number 3 and I started it at 50 degrees, you know, I'm probably not going to achieve 55. And Oliver, you're kind of right in this regard because when you get to higher temperatures, you actually increase the amount of heat energy that's going to be lost to the environment because it will actually emit more because it's a hotter object. That's why if you have if you ever look at temperature decrease on a cup of tea, yeah, if we start off at 100 degrees Celsius, yeah, and you watch the temperature, what I actually should do is it's time, isn't it? We're monitoring a single observation. It's not a repeat. So we're going to have time at the bottom and temperature on the side. And if we monitor the temperature of a hot cup of tea at 100 degrees Celsius all the way down to 25 room temperature, what you see is this kind of graph. Yeah, because it loses heat at a quicker rate at higher temperatures. And so I can agree with Oliver to a certain extent and say the chances are that in this particular experiment, I'm probably not going to achieve 5 degree change. I may achieve a 4 degree change because it's going to lose heat more quickly at the higher temperature. But that actually is completely irrelevant. The reason being is, well, if you were a good scientist and you were going to be measuring a reaction, then doing a start temperature of 20 and a start temperature of 50 is just downright idiotic. That's something you're not going to do. No one would be crazy enough to do that. But the one thing that's borderline, that's the first thing, that's a ridiculous, so I'm going to circle this in red. This is just idiotic. Yeah, you'd have to be an idiot to do that. But the second thing is, well, the starting temperature of 20, trying to get an exact starting temperature for your repeats is another borderline impossible thing to achieve, because all that's going to happen is that you'd spend 20 minutes trying to make the temperatures the same, and you just can't. But in reality, these tiny differences, don't matter. So what that means is, because it doesn't matter, we can realize that the only thing we really need to genuinely standardize is the pressure. Because if I change the pressure, I will change the heat energy change experienced in the reaction. Just to tell you why that is, that's because if you change the pressure, you will change the boiling point and boiling point of any liquids, and that will massively affect how that reaction then plays out. Also, if the reactants are gases, you'll also change the rate of the reaction and therefore change the heat output. So we now pick up, this is the first definition into your list of enthalpy. Because in enthalpy, you pick up boatloads of definitions, and we're going to collect a whole load of those today. But the first one, this is a definition of enthalpy change. So for enthalpy change, the definition is the heat energy change at constant pressure, and its symbol is delta H. This is the original definition. Just to quickly mention, standard pressure, we need to know a value for this, and you guys already know it. You know it from calculations. Standard pressure is 100,000 pascals. Or, I prefer that number because that's what you need for PV equals nRT. Yeah, I prefer you to remember that number more than any other, but you can also say 100 kilopascals if you prefer. You actually need to be able to know how to translate between the two, but that's pretty straightforward as well. Thank you, chemists. Cool. So we've picked up our first definition, and I'm just gonna put that definition in a nice bubble. Yeah. Enthalpy is the heat energy change at constant pressure. That's amazing. First definition. Right. We now need to start picking up some more. Okay, so what other definitions are you going to need for AS level? So the next one is, so you can put definition list. I'm going to put brackets enthalpy because these are very specific. Enthalpy definition list. Okay, and I'm going to do AS. Okay, so the first one, enthalpy. We've now got this one. Delta H, check. Heat energy change under constant pressure. Second, number 2, delta HC. Right, so what does the C stand for? The C stands for combustion. So I'm just going to put underneath that, the C stands for combustion. So we are now specifically targeting chemical reactions that involve combustions. So the reaction with oxygen, and then we're going to make CO2 and water as a byproduct. And actually, that's quite important, really, because I think one of the things that students struggle with when they move from GCSE to A level is the fact that always reactions start to blur together. You know, oxidations seem like they're the same as combustions. Well, they're really not. And so we need to define this very clearly. Now, what I'm actually going to do here, guys, is I'm going to do, what I'm going to do is I'm going to do what's called a frame method. Because when you get to year 13, oh my God, are you going to have a whole load of these to learn? And what I need to do is, so just a lower point, the definition list for AS, there is a second list for A2. And just so you know, when you get there, my lesson title is this. It's the definition list for enthalpy A2. And the reason why I call it the definition list is because there are so many of them. And I'm actually going to introduce you to a couple of those today, just to show you them, just to show you how this, in matter of fact, maybe I'll just give you the extension and just to make you aware of them. But what I'm going to do is, now, if you've got to learn, do you know what I'm going to do? Stuff it. Let's do the AS list followed by the A2 list. So, definition list for AS enthalpy. Enthalpy of combustion. Second one, enthalpy of F, enthalpy of formation. Next one's enthalpy of solution. Enthalpy of solution. This is the heat energy change when you make a solution. By the way, that's not the definition, so just bear with me for a second. Yeah, the next one is delta H hydration. Hydration. Is there any others? Enthalpy of formation, enthalpy of combustion, enthalpy of solution, enthalpy of hydration. Oh yeah, bond enthalpy. Whew. Nearly missed one there. Delta H bond. It's actually, now just to tell you that there's bond dissociation technically. Yeah, I'm going to put bond dis. I'll just put delta HB. For enthalpy of bond, I'll put bond dis. I shouldn't really do it. It would just be delta HB as its symbol. And what that translates to, enthalpy of bond dissociation. Bond dissociation. There we go, bond dissociation. So this covers these. This is your 5 definitions. It's actually 6, of course, because we got the first one. But these are your 6 definitions that you need for AS. Here are the A2 ones. So I'm just gonna. This is see later notes. Gonna zoom in. I just want to show you the list from A2. So A2, enthalpy defs, delta H definitions. You need, this is where it goes nuts, I've got to be careful now. We've got the enthalpy of atomization of AT. I've got the enthalpy, I'm not going to bother with the writing underneath it because I'm going to give you this later on anyway. The enthalpy of lattice dissociation, I'll put lat dis. By the way, actually, just to point out that lattice dissociation is just enthalpy of lat, annoyingly. But I like to put lat dis. Then there's enthalpy of lattice formation, lat form. Then there's the enthalpy of sublimation. Then there's the enthalpy of ionization energy 1. Then there's the enthalpy of ionization energy 2. Then there's the enthalpy of electron affinity 1, and then the enthalpy of electron affinity 2. Then there's the enthalpy of, I've got to be careful now, lattice difference, vaporization, VAP. So you pick up boatloads of these now when you get to A2. And so this is why I call it the definition list, and all of these AS ones still apply. So it's something for you to bear in mind that more of these are coming. Now, what I now do is, because when you look at this definition list, you just look at it and you want to cry. And I totally get it. So what I've kind of designed is a frame method. Do you have a webinar on A2 energetics? EA is electron affinity. That's different from EA. Yes, it's very different from EA, Sian. E little a is activation energy. Holy moly, that's different. Yeah, electron affinity is EA, whereas a capital E little a is activation energy. Good question. Do I have a webinar on A2 energetics? No, I don't at this point in time. Good question, Siab. I haven't got that far with A2 yet. Okay, let's finish off our. So what we want to do, I want to create a definition that will help me answer all of these. Yeah, a single frame that I can apply and just slot in different words. So here's the definition frame. What I'm going to actually do, I am actually going to write them all out, which is really depressing for me. But what I'm going to do is I'm going to put the frame over here. I'll put the frame over here. So the enthalpy, or I don't like the word enthalpy in a definition for enthalpy. I prefer to use heat energy. It has better understanding for me. The heat energy change when, enthalpy of neutralization. There's another one, guys. I've suddenly realized there's another one for AS, enthalpy of neutralization. I'll add that to the AS list. That's where the A2 list is going to bug me. Let's move the A2 list down. See, obviously I have to just kind of pull these out of my head. But I'm just going to add enthalpy of neutralization, delta H neut. Neutralization. Neutralization. I like it. Okay, so here, what I'm actually going to do is I should do this as a nice easy frame. So the heat energy change when 1 mole of dot, dot, dot. First word. Yeah? So this is going to apply to everything. So the heat energy change when 1 mole of, yeah, I'm actually need to put this in a setting because I find it quite hard to leave the blanks in my mind. Let's apply this to combustion. So the heat energy change, what I'm going to do is I'm going to frame in purple, and then I'm going to add my other words in to show you the difference between them, and then switch back to purple. The heat energy change when 1 mole of, let's do combustion. The heat energy change when 1 mole of a substance is completely burnt in oxygen to form CO2 and H2O only. Switch back to purple. All under standard conditions. Has my pen changed color? Yes, it has. All under standard conditions and standard states. Right, so you can clearly see that there is a commonality. Let me show you another one. So that there is your definition for enthalpy of combustion. The heat energy change when 1 mole of a substance is completely burnt in oxygen to form CO2 and water only, all under standard conditions and in standard states. And I've said in there, I added in an in standard states. You can add that in if you like. They won't care. And standard states, they won't care. Yeah, if you want it, you can. Right, let me show you another one. Let's do enthalpy of formation. Okay, the heat energy change when 1 mole of. The heat energy change when 1 mole of, notice the similarity. It all starts the same way. Right, now I need to add in my bit for formation. When 1 mole of, switch to green, when 1 mole of a compound is formed from its elements, from 1 mole of a compound is formed from its elements, all from its elements, switch, all, damn it, switch to the wrong color again, all under standard conditions and in standard states. Isn't that cool? There's only really one adaptation. And don't get me wrong, you need to be able to know those adaptations. But in reality, it's about a routine, isn't it? Let's do the next one. Let's do, I've done combustion, done solution. Okay, solution. So, the heat energy change when 1 mole of. The heat energy change when 1 mole of. I hope that you guys are writing all of these down as well. Yeah, I don't want you to be copying and pasting if you're doing this on digital notes. You should be writing these down to get you into good routines. The heat energy change when 1 mole of, switch to green, I want to try and keep consistency. Heat energy change when 1 mole of a substance is dissolved in excess water. Is dissolved in excess water dissolved in excess water to form its, that kind of covers it, to be fair, dissolved in excess, substances dissolved in excess water. It's to form an unsaturated solution. Forming a non-saturated solution. You don't want to hit saturation. Yeah, you're trying to avoid it. That's where, can I just point out, I don't actually think you need the excess water bit. Sorry. You don't need the non-saturated because the excess water covers it. I don't actually think you need that extension. I tend to add it because it's a pattern that I've been taught. I'm not entirely sure if it's needed. All under standard conditions and in standard states. All under standard conditions and in standard states. Cool. Now just, yeah, okay, we'll keep going. Let's do the next one. Enthalpy of hydration. This is a tricky one, this one. Enthalpy of hydration. The heat energy change when 1 mole of the heat energy change when 1 mole of gaseous ions react with excess water to form aqueous ions. Now, this one's an unusual one because they're not in standard states, and we have actually covered that there. So we have to be really careful. This is one of the ones that breaks a rule. Yeah. Now, I'm not going to lie, though, all under, because I'm pretty sure, or in fact, I know I'm right, in saying that if Winkit, does the enthalpy change for combustion need to be complete combustion? Yes. Yes. Oh, no. Hang on a minute. No, it doesn't actually need, because you're stating it in other places, Winkit. You're stating completely burnt. Yeah, completely burnt. That's the bit that covers the complete combustion. And in excess oxygen, I should say in excess oxygen. You don't actually need it because you've said completely burnt, but I think there's value in adding the excess. Add the excess to your definition, because that covers complete combustion. Yeah, is completely burnt in excess oxygen to form CO2 and water only. And that also covers your complete combustion as well, Winkit. Yeah, I'm pretty sure my definition would score me all my marks, but I would like to add in that word excess. Thanks so much, Winkit. I think that's worthwhile adding. Complete combustion. Yeah, that's what that is doing. Yeah, I don't want to add that to my definition because you don't need to. But that bit there, complete combustion, and that is also being supported with the CO2 and water only. Yeah, because if it's incomplete, you won't get CO2 and water. You'll get carbon, you'll get carbon monoxide, all that jazz. Now, in this particular definition for hydration, if I say all under standard conditions, yeah, that's true because it's pressure. Yeah, that standard conditions literally means under constant pressure, but they prefer you to stay standard conditions. Yeah. And if I now add on, and I'm going to do this in red, if I then said all under standard states, then technically I'd like to lose a mark because these aren't standard states. These are actually in a gaseous ion state, which is definitely not standard. Yeah, but I'm pretty sure it says on the mark scheme, ignore comment on standard states. Yeah, so if you write it, I don't think you'll lose any marks. And I always think that it's better for me to teach you a routine of writing the same thing every time, because I'm pretty sure you score all the marks anyway. All under standard conditions and standard states. I will just put standard states. I'm pretty sure that if you say it, it won't matter, but I will just say that bit there wouldn't be included in this particular definition because they're not in standard states. So for example, the equation would be sodium gaseous ions, would react with water to form Na plus aqua. There's the definition of that. That's the definition in an equation form. I'm going to give you an equation for every single one of these, in fact. So enthalpy of combustion would be something like, right, the equation would be 1 mole of methane with oxygen to form CO2 and water only. Right. All in their standard states. Gases, gases, gases. Ooh, water. Isn't that important? Look at that. There's a bizarre standard state. If you burn methane, you're not going to get liquid water, but the definition demands it. Yeah, definition demands this. Yeah, demands L state symbol, because it says in their standard states, and water's standard state at 298 Kelvin is liquid. Definition demands this. Yeah, state at 298. Yeah, demands this. Yeah, right, balance it. Now at this point, just to mention, I cannot double the equation. Yeah, if I balance this, 1 carbon, 1 carbon, 1 carbon, 1 carbon, 4 hydrogens, 4 hydrogens, oxygen. Oh, 4 oxygens, 2. Okay, done. Now that equation is correct. Can I just emphasize, in the definition, it says the complete combustion of 1 mole of. This is where, do you remember I said to you guys that you could balance equations with halves? Yeah, when I got told that in school, I nearly wet myself. It was amazing. I was like, oh my God, I can balance with halves. It's the best thing ever. And in reality, they don't really care if you double it or not, except in this place. Because if you do the next equation, if you do ethane, I never like molecular anymore. Molecular's dead. We're going to do ethane. We're going to burn that in excess oxygen to form CO2 and water only. Yeah, state symbol's got to be applied. Ethane's a gas, oxygen's a gas, CO2's a gas, water's a liquid. Balance it. 2 carbons, 2 carbons. Hydrogens, 6 hydrogens, 6 hydrogens, oxygens. Oh, I've got 7. Now, certain students hate halves, 3.5, and they'll double it. You're not allowed to, guys. You are not allowed to double it, because if you double it, you're not burning 1 mole. You're burning 2. It's not allowed. The definition states when 1 mole of a substance is completely burnt. Yeah? So that's really important. In this particular scenario, you are not allowed to double. Yeah, you've got to keep it as 1 mole here. Yeah, and that's going to be 3.5. That's then going to be 2, and that's then going to be 3. That now is the definition for the enthalpy of combustion of ethane. Yeah, it's important that I mention this to you guys. How are we doing with our definition list? It's a nightmare, isn't it? Let's have a look at enthalpy of formation. The enthalpy change when 1 mole of a compound. Compound. Look at the key word here. Right, I need to make a compound. What compound am I going to make? Let's make ethane. So I'm going to do C2H6. I hate molecular. Ugh. What am I going to need for this? Well, ethane's a gas at room temperature. Standard conditions in standard states. I need carbon. Oh, what's carbon's standard state? It's a solid. Now I'm going to add hydrogen to it. What's hydrogen's standard state? It's a gas. Right, now I need to balance it, and I cannot change that number 1 because the definition says 1 mole of a compound is made, and that's 1 mole. So I'm going to need 2 of those, and I'm going to need 3 of those, and there's my definition of the enthalpy of formation. Enthalpy of solution. The enthalpy change when 1 mole of a substance, 1 mole of sodium chloride, solid in its standard states, is added to excess water to forming a non-saturated solution. All understand, right? The saturated solution, I'm going to form, it's aqueous ions. I've made a mistake. And that's where it's so important to know your equations. I apologize. There we go. So forming a non-saturated solution of its aqueous ions. Of its aqueous ions. Non-saturated solution. You don't need that because it says excess water, so technically you can delete that. Make it easy for yourself. A 1 mole of a substance is dissolved in excess water, forming a solution of its aqueous ions. Forming a solution of its aqueous ions. That's allowed. That's totally okay. You've said excess water. It ticks the box. And there's then the equation to go with it. Yeah, next, hydration. There we go. 1 mole of gaseous ions reacts with excess water to form aqueous ions, all under standard conditions. No standard states because everyone's outside of the standard states. Will it be the same for all the equations? Can we write 7/2? Sian, you can write 7/2. They're not going to like you very much. Can you not? I don't like it. It's rubbish. They want to see big numbers. Just do the big number and then a fraction. Sorry, technically you're allowed, but they won't like you, Sian. I'm being an exam prep teacher there rather than a chemistry teacher. You can use 7/2, but I don't like it. It's disgusting. I hate fractions. Yuck. Next, bond dissociation. Okay. Delta HB. The enthalpy change when 1 mole of. I love these definitions. The enthalpy. I'm just gonna enthalpy change. The enthalpy change. No, don't like that. Garbage. You can put it, by the way. It's allowed. The heat energy change. By the way, you're not allowed to say heat change. You'll lose it. The heat energy change when 1 mole of. Change when 1 mole of a covalent bond. 1 mole of a covalent bond. Of a covalent bond is broken, forming gaseous atoms. Gaseous. Oh, that was interesting. My pen went a bit wonky. Oh, that's bad news. I recently. Oh, that's interesting. I recently put a screen protector on my laptop. See, look, it's fine there. Forming gaseous atoms, all under standard conditions and in standard states. I'm going to switch back. All. Oh, it's doing something really weird. It's not liking my writing. Oh, I'm just going to quickly close it. It's already synced up. So if I close that down and reopen it, I don't know what time this lesson finishes. Lol. The answer is in 10 minutes. All under, it's not liking it. All under standard states. No, hang on a sec. Gaseous. No. All under standard conditions. And once again, we've got a funny situation here, guys, with states, because we're forming gaseous atoms. Well, that's not a standard state, all under standard conditions. I will put and standard states, but I'll cross that off and say that's not needed. If you say it, I'm pretty sure what they will do is they will just say, please ignore standard states. But that technically does not appear. I wouldn't include it in my exam. Let's write an equation for it. Okay, so... this is going to be interesting, isn't it? Because we need something like hydrogen gas. 1 mole of a covalent bond is broken. By the way, they've all got to be gaseous. Yeah, because you can't break a covalent bond. There you go. That's clever, isn't it? Now, just to tell you, by the way, that you could write 2 H's like that, but I think there's better understanding to look at it like that. That actual equation would actually look like this in reality. If you're interested, it'll actually look like that in reality, but it's the same equation and they'd allow both, just so you know. Why a covalent bond exclusively? Because ionic attractions are not actual bonds, Jim Joe. A bond, this is very, very specific. Yeah, bonds in chemistry are covalent. Remember that. There is no such thing as an, I don't even like saying it, it gives me the creeps. Yeah, there's no such thing as an ionic bond. It is an electrostatic attraction between oppositely charged ions. That is not a bond. Yeah, if you have an electrostatic attraction, that's this attraction here. A covalent bond is a physical overlap. That's a real bond. Yeah, hydrogen and hydrogen, they are literally crossed over and their orbitals are quite literally fused. Yeah, that's a real bond, whereas the electrostatic is just an attraction. And in this case, we're talking specifically about covalent bonds. Yeah, good question, Jim Joe. Well done. Will it be the same for all the equations? Not to be able to use, not to multiply. Yes, that's correct. If you double it, okay, great example for combustion. Let's say I did this. Yeah, to form this and 4 of those. Right. This is a really clever question because that there is not the enthalpy. That would be, let's draw it out. Let's draw it out into bonds. What have we done? We've split that to form this. Yeah, we've broken 4 bonds. Yeah, that will actually be, that equation there is the enthalpy change for the bond dissociation for BD of the CH bond times 4. So if somebody said, write the equation, look at this equation and balance it to be the bond dissociation, what I would do is I would put 1/4 of that. Unfortunately, that would give me 1/4 of a mole of that, and it would give me 1 of that. There we go. Isn't that a nightmare? That technically is now bond dis. It's a nightmare. In reality, you wouldn't do that. What they'd do is they'd give you this value. Let's call that plus, I don't know, 1200. And then what they would do is they'd give you that value and say, what's the value of this? And you'd just divide that by 4 to give you plus 300. Yeah, that's how, but this isn't a definition of covalent bond, also electrostatic attraction. Oh, yes, it is. The electrostatic attraction between the shared pair of electrons in the 2 nucleuses of the atoms, yes. But there is a physical joining. The orbitals actually blend. If you looked at a hydrogen atom looks like this. It's a sphere because its electron configuration is 1s1. Yeah. If you then take 2 hydrogen atoms with this sphere 1s1 orbital, and you now put them together to form a bond, you form this. You form that. Yeah, they actually blend together. And so there is a physical melding of orbitals. Notice that it's even as well. Yeah, if you do that with hydrochloric acid, oh, that's complicated. If you do that with hydrochloric acid, you have a circular 1s1 for the hydrogen. Yeah, I quite like doing it like that. It's quite funny. Look at that. Isn't that neat? Yeah. If you then look at chlorine. Chlorine is number 17. 1s2, 2s2, back to the skip over 2p6, back to the beginning. 3s2, skip over 3p5. So the outer energy level is in oh, you're not going to know this stuff yet. But anyway, it's a P. Oh, it's really awkward. I don't really want to show you this. Yeah, it's actually in this scenario, like that. And what happens is when these guys join together, it's because it's in a hybrid state. Don't really worry about it too much. What's going to happen is that's going to physically blend. Yeah. Yeah, it looks all a bit weird, doesn't it? Like that. And those two will physically join together. Yeah, into a single orbital, and it'll blend HCl. And it wouldn't be even either. It would be unevenly distributed. If you wanted to look at that bond specifically in terms of its electron distributions, it wouldn't be even. What it would look like would be this. Like that. The reason being is our chlorine's more higher in electronegativity. Don't worry about it. I don't want to get into that. I've lost it. I'm sorry. Shouldn't have done all that. It's nice to do it though. It's cool pictures. I'm going to delete all that stuff. Delete all that junk. But it's nice to mention it in terms of covalent bonds, yeah. And I know it's odd, but you just got to accept it, folks. I'm nearly at the end of my lesson. All we've done, and we've got one more, enthalpy of neutralization. Okay, delta H. Have I changed my color? No. Delta H neutralization. Guys, I've realized I've gone on. I'm just going to do neutralization. I'm actually going to leave the lesson at this point. And what I'm going to get you to do is, I'd like you to look up that particular definition. I want you to see, in fact, you know what? I'll do it with you. I want to show you that the internet is a great resource. It is. But it's also full of junk chemistry, which is really not very useful. I want to show you how this differs from what I'm writing. Enthalpy of neutralization. Yeah, there we go. The heat energy or enthalpy. Oh, that's annoying. See, immediate incorrect. You can't say heat without the word energy. You can't say the word energy without heat in this scenario. So it's wrong immediately. The heat or enthalpy of neutralization is the heat evolved. No, it's the heat energy evolved when an acid and a base react to form salt plus water. And that's completely incorrect. What a load of garbage that is. Well done, internet. That's great. There we go. Look at this one. The enthalpy of neutralization is the change in enthalpy that occurs when one equivalent of an acid and one equivalent of a base, oh my goodness, undergo a neutralization reaction to form what salt and water. It is a special case where the enthalpy, it's defined as released when the formation of 1 mole of water. Now that's also, let's now convert that into the good definition that we're going to use in our exams. Yeah, so the enthalpy change when 1 mole of the enthalpy, I'll switch back to purple. The enthalpy change when 1 mole of the heat energy change. Heat energy change when 1 mole of, and we realize 1 mole of, the 1 mole is water, ... 1 mole of, switch to red, 1 mole of water is formed when 1 mole of acid, the thing is, no, notice that they didn't say when 1 mole of water is formed when an acid reacts with a base. All under standard conditions. Now, do we apply standard states here? No, they're all aqueous. All under standard conditions. But if we write it down and standard states, they will ignore it. Standard states. But I would probably, in my exam, I wouldn't write that down because I know that it's not needed. Let's write an equation for it. Hang on a sec. HCl. Let's change different color. HCl reacting with sodium hydroxide to form salt and water. But the key thing is 1 mole of water is being formed in a liquid state. Yeah, in its standard states, and they're all aqueous. That's why they're non-standard, because an acid needs to be in solution to be able to do this. Yeah, neutralization. So that they're not standard states, because the standard state for HCl, by the way, is a gas, and the standard state for sodium hydroxide is a solid, just so you know. And the standard state for sodium chloride is a solid as well. So they're not standard, so we ignore that, but we must make 1 mole of water. So if I now do something like, let's do calcium carbonate plus sulfuric acid. Yeah, if I now do that one, I'm going to form calcium sulfate, yeah, plus CO2. Have I just gone and made a mistake? That's really irritating. I've made a mistake. So hang on a minute, I'm going to change that. You'll see why. Yeah, let's put HCl. No, I don't really want to do that. I want something that's going to make 2 moles of water. Yeah, I can do that. Calcium hydroxide. I've realized my lesson's overlapping. Calcium hydroxide plus H2SO4. Yeah, I'm going to form calcium sulfate and water, and I will make 2 moles of water. Right. So what would be my that's incorrect. That's the enthalpy of neutralization times 2. So I'd have to put half a mole, half a mole, half a mole, and 1. There's the enthalpy of neutralization, because I'm forming 1 mole of water. And that brings us to the end of our AS definitions. We've ticked them all off. I haven't managed to do. So we recognize we can certainly have done that one and that one. Next lesson, I'll pick this up and we'll do understand when enthalpies can't be measured. But we've worked through our definitions today, folks. I know they're a nightmare. What I can tell you is in your exams, you're going to get 2 of these definitions, and they're worth 2 marks each. So I'm going to end the lesson there at that stage. I'm actually going to activate my camera now, and hopefully my laptop doesn't crash. Excellent. Good. And go back to StreamYard. I know I'm running no probs. Let's go back to this one. Give me the front camera. Give me the front camera. Start cam. Give me the front. Yes. Right, guys. It's confusing. Lol. He might just do AS energetics for 2 hours. Lol. I'm sorry I've overlapped, guys. Guys, I will leave you guys be. Have a nice rest of your day, guys. See you later.